that note, when I said yes to this presentation, I thought it would just be 20 OT geeks. So I had to moderate my presentation a bit. Hopefully I moderated enough to be understandable for the main audience. So I work as an industrial solutions architect in the business unit, in the manufacturing of the blades, in Aalborg, in the global department. So before jumping to the HighByte use case, I would just like to present the company first. So we are owned by 100% by Siemens Energy AG, and we are the biggest manufacturer of wind turbines, at least offshore. Just some key facts. We have 137 gigawatts globally installed. Our company is on around 29,000 people. Our revenue was 9.1 billion, and our current backlog is around 42 billion euros. We have sales offices around the world, and then we have our main engineering units in Europe and India, and then we have manufacturing sites across the world. So the biggest ones again in Europe, but also supporting the American market and the APAC market, both in India and China. Our business consists of three main business units. So we design, we sell, we design the wind farm, and we manufacturing, and we install onshore wind turbines and offshore wind turbines. And then finally, we also service the turbines, not only our own, but we also service other manufacturers as well. So yeah, that's the last and third business unit. Just to give you an introduction to one of our latest products, this is the 14 megawatt wind turbine. The rotor diameter is 236 meters, and the blade length is 115 meters long. So that's the business unit I'm in. That's manufacturing of the blade, which I will talk a bit about for the use case. And then installed on the three blades are then installed on a cell that's converting the mechanic energy into electricity. And then we ship the energy to shore. Okay, so that was the end of the pretty corporate slides. And I'll now show you perhaps a bit messy technical slides on how we use HighByte in Siemens Gamesa. So before deep diving into that, I just want to showcase the traditional enterprise architecture stack with the business driving the data layer, which drives the application layer, which finally drives the technology layer. And some of the challenges we have across these layers is on the business side, we are still a fairly young industry, and we have been in a constant arms race with our competitors always releasing new products on the market, trying to minimize the levelized cost of energy, that is building bigger and bigger wind turbines. So we never keep a product more than a couple of years in the production lines before we pretty much have to change out our entire line and start from scratch. So that means our processes are not always that well standardized, and our processes between our business units is also different, and also between our plants. So producing a blade is very much different from producing in a cell. On top of that, we are currently merging with Siemens Energy and their landscape and their processes. So that also gives rise to a lot of changes. On the data layer, on the shop floor, we have custom tooling that we regularly change out. And we haven't got around to standardize the data models at the shop floor. Also, our master data models are constantly evolving. On the application side, with the merge of Siemens Energy, we're also changing out our MES and ERP. And we're also changing out our data warehouse concept of these. And on the shop floor side, we have a high variety of protocols to devices and applications. Then finally, on the technology side, we are changing out our client provider going towards the Siemens Energy setup. Our network is also quite challenging. Security, we only run in private networks, only private endpoints, etc. And routing of network can also be a bit challenging in a 400-meter long production halls, owing having 2 multi-layer switches at each corner. Also, Wi-Fi 4G is a bit difficult, having 150-meter long steel structures constantly moving around the production halls. They kind of, it's difficult to get a stable network connection. So with that said, we needed a product that was independent of cloud provider, independent of which OS solution we run on which edge device we run on, was independent on protocols. It had to connect to a lot of different protocols. And we also needed the ability to use store and forward because we don't always have connectivity. And we needed to standardize all that into a common data layer. And for us, HighByte solved that case. So I'll show you how we use HighByte in general on the next slide. It's intentionally a bit messy, but that's also to show you how we use HighByte as this Swiss Army knife to solve that specific use case under those specific circumstances. Right. So we have HighByte installed differently on each side. So of course we have the classical main server approach, where we have a redundancy main server running virtual machines, running different Docker containers using HighByte. These then go outbound and connect to various PLCs on the control network or OT network using OPC, SQL, or whatever protocol they have to. At the same time, the data payload might be so big, or we might not be able to, as John explained, encrypt the data. Not always we have the ability to have our suppliers to encrypt the OPC UA server. Then we put HighByte on the control network behind the secured segregation of VLAN, and then we can encrypt the data going upwards. Maybe we don't always want to push all the data, maybe we only want to push the aggregated data, so that also makes it nice and easy to having HighByte running on a control network just next to the asset. Then, as I said, it's not always possible for us to get our assets connected to a corporate network due to various reasons. So we also have HighByte installed on an IPC, on a gateway, and then connected using 4G. So for instance, it could be on an IPC, running HighByte in a container, connecting to the OPC UA, and then publishing up the data. So if you go up the stack, or up to the cloud up here, then basically we just try to land the data in a JSON format, which is nice and easy to read. And we use mainly MQTT, Spark B, or just classical REST API. Then we save the data to our either Historian, Datamart, or into our cold storage, or PLOP. On the front-end side, we use a combination of Power BI, more custom RStudio dashboards or Shiny dashboards, together with Python, and of course we also use Grafana. We are currently trying to figure out how to connect HighByte with the what we call the Holy Trinity, like MES, ERP, and PLM. I have a bit more on that a bit later. Yeah. Okay, so I also wanted to go through a specific use case to showcase some of the different features in HighByte. I won't go into too much detail into them, but I guess, John, you will showcase how to do models, conditions, and so on in the demo. So hopefully this should make sense later on for you guys. So when we produce a wind turbine blade, we start off with a lower mold, then we put glass fiber in, balsa wood, etc. Then we put a mandrel on top, then we pack the mandrel, and then we put an upper mold on top, and then we infuse resin through the fiberglass and balsa wood, and then out you get a casted wind turbine blade. So the process engineer responsible for casting, they might be interested I want to know the casting temperature for that specific lower mold, for that section, and I want to see it for this specific production order, or I might want to see it for the last 200 production orders, so that I can do XXX. So how we went about to do that is we start out by connecting to the assets, so the mold control system. That's one that's controlling the process of infusing and curing the resin going through the mold. We connect to that with OPC UA. Then we have HighByte installed on the edge in this case. Taking that in, that data, model it so it fits in with our definition of the unified namespace. On top of that, we also put on a deadband because we're not interested in sending flickering data. We only want data that changes more than a threshold. Then on the cloud side, we have HighByte connected to the broker as well. And then we make a model and an instance of that unified namespace. And then we're taking the definitions of the unified namespace from our data mart. So we have 3 normalized SQL tables that we use for this use case. So the one is for the UNS definition. So that lives both in the broker, but it also lives in the data mart itself. Then on top, we need the context for the data payload. So that is what is the production order, what is the main set point, what is the operation mode, etc., etc. We keep that in a normalized SQL table because, to make the data analytics a bit faster. You push all these 3 tables into SQL, and then you can combine it into a view and visualize it in Power BI, for instance. It's also important to say this is just one use case. So I could easily also just take my unified namespace, again, connect HighByte to it, and then I'll just flatten out all my topic structures, and then I just drop it in a Parquet file in blob storage, and then pick it up with Apache Spark and to analyze it if I needed to do more big data analytics. And you can support both pipelines, right? As long as you just have it one place, that is unified namespace. So the first thing is on the edge is to connect to the PLC and then push it into the unified namespace. So if you start with the ISO 95 definition, that is enterprise, site, area, line, and cell. So we use MQTT Sparkplug B, and that has the definitions of group ID and edge node ID. Basically, there's 2 ways to build the ISO 95 model in using Sparkplug B. There's and I'm looking at you, John, because I'm not sure. There's a Paris method and there's the Schultz method, right? Yeah. And we're using the Paris method because we are not able to put a broker at the line to build it up. So that's why we consolidated at the cloud using the Paris definition. So basically, building the first ISO 95 model is then, for us, the group ID is then Siemens Gamesa, Aalborg. That's where we produce the blade. Segment 2, that's our area. Then there's the line, that's blade casting. And then there's the cell, which in this case is the B97 blade, just a bit smaller than the one you saw before, 97 meters long, position 1. Then under the ISO 95 model, we define different equipment models, and we try to utilize ISO 88 for that. So one module is the heating modules, and another module is then the temperature module, which we'll talk about in this use case. So building that, on the left side, we have the OPC UA server. Everything is in PID diagrams because automation engineers, they love their piping and instrumentation diagrams. So 055, I think that's like the TT 055, that's the forward temperature on the heating boiling unit on a lower mold. Probably. I wouldn't know. But, so if we put it into a context module, it might be the heating module, then the lower mold, then the power zone, then the boiler, and then you put it in. So you have like the entire context, so everybody knows exactly what that tag means. for our use case, we'll be looking at the temperatures. So L1, that's the lower mold. 1 means it's section 1, and TT001 is just the placement of that temperature transducer. So in our case, it's down here. And then, as John showed before, you can even build that even further, putting in the engineering unit, which is degrees Celsius. We also like to put in the PID tag, because so then the automation engineer can look at the unified namespace and see, okay, that's the 0055, I know what that is. And we utilize these equipment modules on like the same cell for the different on the same site, and going on a different site. So this is Siemens Gamesa, Hull, which is in UK. We have the same definition of segment 2. The line is the same, it's plate casting, but now we're producing the 108 meter blade, which has the same temperature module definition, but the heating module, I think, is different. So we can reutilize the same models across different lines, and then just change out if we go from a boiler concept to electrical heating concept, for instance. So that makes it very nice that you just define the model once, and then you can have it standardized across all your different assets across your enterprise. So once you have landed your data in the unified namespace, it's time to build the data pipeline. And before we do that, we just need to define our schema. So first of all, we have the ISM95 model defined again in normalized tables in SQL. So we have a specific cell ID, and then each tag in the temperature module then has its unique tag ID, and then we have the reference data. Is it the lower? Is it at the upper? Is it the section? Is it, and which TT is it? On top of that, we also need the context of the data. So we use the context for many things, not only for the temperature data. So this is a generic table. So again, for this specific cell ID, what was my start time, end time, for this production order, for this operation mode, for this set point, etc., etc. So if I needed to calculate my cycle time, it's just be a simple group by. Finally, we have the actual sensor data that goes into the sensor data table with a unique combination of tag ID and time, and then the value, as you might know from the ignition historian module. And then on top, we just pass in the lookup ID, so we can get all the context of data for that specific data point. And the main reason we do this is because this table here has a tendency to fill up quite fast. So if you normalize the data tables, we remove duplicates, but also the group bys that we need to do is on the context data or the sensor placement data, and then simply the operation will just be a simple lookup in the sensor data table. So from the process engineer's view, they have like one view where they have all the data they need. Which site was it, which mold, the time, the production order, the operation mode, set point, where is it in the mold, and then the actual value. And also it makes it super easy for them just to aggregate the data for, let's say I wanted the average temperature for section 1 in the lower mold for the last 200 production orders, and I want to correlate that with my quality data. And they can do that in Power BI because we built everything up in a data mart concept. So it's really easy for them to do data analytics. So if you start building this in HighByte, so this is HighByte in the cloud. So the data model itself lies in the SQL definition. So the model itself in HighByte is quite easy. It's just tag ID and value. And then the reference is the UNS lookup, or the UNS definition, or sensor placement definition, that we just put in as a dynamic reference. The input of the data comes from the SparkPlug B broker, or the unified namespace, as we put in here, and then we use the references from the SQL table to look up in the UNS definition. So you can see here it says this cell, this lower upper, this section, this TT. So that means, for instance, that tag ID 12, which has a value of 20.9. That's the that would be the TT012 for section 1, lower mold for Aalborg for the B97 cell position 1, for instance. And then tag ID 10,000 might be for Hull or whatever. Then the next thing is to push this instance to a flow. And in the flow, we use the timestamp of the module as a trigger. So we have like an event-based architecture. So whenever the edge decides to send up a new temperature, because it makes no sense to send a temperature if you're not casting. So it's the edge that decides when the cloud pipeline is running by having this event-driven trigger. On top of this, we compress the payload. So also we have the deadband in place, but we also compress the payload because we don't want to save the same value again and again and again. Again, it's similar to the way you would set up the historian module in Ignition. That's also the reason we have the time buffer. And then basically we just have to push in the timestamp to the payload. So that's what sits in here in the pipeline. And then find the lookup to get all the context. So that could be tag ID 2000 might means this production order for this set point, for this operation mode, for this cell ID. And then finally you just push that to the sensor table. Okay, so we have 3 different tables which we can now bring together in one view, which makes it easy for the process engineer to do the visualization as they need. So we have one view with the sensor placement, not only for that specific cell, but for all the different sites. They have all the context they need, so they need the production order, which we call blade ID. They have the operation mode, which is the what's called system step. And then of course they have the placement of the TTs and the sections. So in this case, the process engineer, they wanted to showcase the temperatures for each different section, and then for the lower and upper mold, and then in the legend, they just push in the TT value. And they can see here that, for instance, the temperature for when the infusion starts for that specific timestamp would be this and this. So where it really makes sense is that what the process engineer is interested in is, for instance, the curing temperature and how that relates to the glass transition, how well the fiberglass has been cured. So what they want to do is basically they just want to calculate the average of the temperatures for each section for both lower and upper mold. They want to do that for the last 200 production orders, only for the operation mode's curing, which might be 85, and then correlate that with the quality data and see if there's any correlations with that model. And they can do that in Power BI because that's how we set up the schema, and they can do it in real time. And this is just showing the same picture in a bit bigger format. So as I said, this is just one way to build a data pipeline, and having the data in a unified namespace for us is just as easy just to flatten out the topics, push that to a Parquet file, and then bring it up in analytics and Apache Spark, and even also just to patch in the context for that specific Parquet file. So the data scientists have everything in their Spark pipeline for the analysis. So just a bit on the future of where we are going. So currently we are looking into moving the broker to a demobilized zone. So we have our own data center. So we probably keep it completely on-prem, on air-prem. Then we're also looking into splitting out the namespaces. So Spark B is really cool, but it's not that well with enterprise applications, such as SAP digital manufacturing. So we're looking into copying that spark plug namespace into a flat vanilla namespace, and perhaps even move those into different brokers due to cybersecurity. So like the sites are only connected to the on-site broker, and then the enterprise applications are connected to a different broker. We're also looking into how to do the DevOps. So on the cloud, we're using Azure DevOps, and with the new release of 3.4, we're just starting to build those CI/CD pipelines using environment secrets. On the on-prem side, it's a bit more tricky because we have no internet connection whatsoever. So I think, we're currently looking into using Ansible for our CI/CD pipelines, and then kind of trigger manually from our Azure DevOps tool. Then we also, as I said, we're merging with Siemens Energy, so we're changing out our ERP and MES system, so that's being SAP, S4HANA, and digital manufacturing. So currently we're just investigating in how to connect digital manufacturing to the flat vanilla namespace. At the same time, we probably want to use some REST API calls, because sometimes it's just easier to build things in REST than pure MQTT. At the same time, Siemens Energy is really big on the AWS Sidewise, so we're also looking into how to merge those two different data models. And finally, on the data warehouse concept, we're moving into Snowflake as well. So we're just figuring out how to change our data pipelines using Snowflake instead. At the same time, keep in mind our legacy systems and keep them operational. I think that's more or less it. If you have any questions also after the presentation, then feel free to write on LinkedIn.
Cool. Thanks, Henrik.